the radial functions, in general, if you examine the way these are written, you'll find that you have, well, as with all wave functions, you have a normalization constant. Okay, there's a term there that says r raised to the power L. So if you have an s orbital, that just disappears. R to the 0 is 1. But if you have p, d, or f orbitals, r to the L is, you'll see that. So if you have a p orbital, you'll see an r there. If you have a d orbital, you'll see an r squared there. And then you have a polynomial in r, and that polynomial, the degree of that polynomial is L minus n minus L minus 1. So that tells you how many nodes you're going to have in your radial function, how many radial nodes your wave function has, because the roots of this polynomial will be values of r, where psi is going to be equal to 0. Okay, so, and the degree of this polynomial happens to be equal to n minus L minus 1. Okay, so a radial node is a spherical surface where the probability of finding the electron is 0. That's where the polynomial goes to 0. You'll also notice that when r is 0, okay, your radial function is 0 unless it's an s orbital, because in an s orbital this term does not appear. Okay, so if you have a p orbital, a d orbital, an f orbital, at the nucleus the radial function is 0. Okay, so r equals 0 at the radial function is 0 at the nucleus for non-s orbitals. In fact, you'll find that for s orbitals, maximum value for the radial function occurs at the nucleus. The most probable point among all possible points for an electron to be in an s orbital would be at the nucleus. It's not the most probable. The most probable distance is not 0, simply because when you're talking about distance, it's not that. You have to take into account that the further you are, there's going to be more points that would be at that distance. Okay, so if you're looking at most probable distance, you have to look at the radial distribution function. But if you're just looking at probability, comparing probabilities point by point, then you look at the value of r squared itself, just the radial function squared. All right, so how do we determine the nodes? We just examine the polynomial and find the roots. So for example, if you have a 3s orbital, okay, the polynomial term would look like this: 6 minus 6 rho plus rho squared, where rho is 2zr over a naught. So here's your r, it's a polynomial in r. Z is just the atomic number, a naught is the Bohr radius. So just find the roots of the polynomial. 6 minus 6 rho plus rho squared equal to 0, quadratic polynomial. And you'll find, so here it is worked out, negative, the b here is negative 6, right? Negative b plus or minus square root of b squared minus 4ac over 2a down here. A is 1, b is negative 6, and c is 6. And if you carry out that calculation, you'll find that your nodes occur at 3 plus or minus square root of 3. Okay? And what's 3 plus or minus square root of 3? That will give you 2 nodes. Okay? So if this is 3, 3 plus square root of 3 would be 1 radial node. And 3 minus square root of 3, that's the other radial node. You have 2 radial nodes for the 3s orbital. Okay? In fact, the degree of the polynomial is n minus L minus 1. 3s, n is 3, L is 0 for an s orbital minus 1. That gives you 2 nodes. You have a quadratic polynomial term for the 3s orbital. Is the part of the wave function that depends on theta and phi. Generally, what you'll find is that anytime you have a spherically symmetrical problem, by that we mean a problem where your force, our potential energy depends only on the distance from a given point. So potential energy is a function of r only. You'll find that it's convenient to use spherical polar coordinates because you'll be able to write psi as simply a function of r times a function of theta and phi. And we already know this part of the solution. That's just the spherical harmonics. Okay, the same solutions we found when we did the particle on a sphere. The nodes resulting from y from the spherical harmonic being equal to 0 are known as your angular nodes. And you'll find that for your real orbitals, the number of angular nodes will just be equal to L. So that means for a 2p orbital, you have one angular node. L is equal to 1. What about a 3D z squared orbital? You're going to have L equals 2, so you have two angular nodes. Let's look at 3dz squared. Okay. There's your two angular nodes right there. There's a conical surface right there. Theta equals something like 57 or 53 degrees. I think it's 57 degrees. And there's the other conical surface. That's the other node. Theta equals 180 minus 57. I think it's 57 or 53.7. We'll check that later. Okay, but anyway, you've got those two nodes. Constant value of theta, simply a conical surface centered on the z-axis. So, and those are your two nodes right there in this three-dimensional isosurface representation. So you have that cone up there and that cone down here. Okay? So how many angular nodes are we going to have for a 2pz orbital? L equals 1, so one angular node. Okay? And if you remember your 2pz orbital, your xy plane is a node. And xy plane simply means theta equals pi over 2. Theta is the angle that you form with the z-axis to get to the point. So that's the angular node for a 2pz orbital. 3px orbital, again, L equals 1, you get one node. 4dxy, for a d orbital, L equals 2, you're going to get two nodes. Okay. I want to take a look at those again. Oops. There's 3dxy. There's your two nodes right there. The xz plane and the yz. Okay, so here's your xz plane, that's one node. And there's your yz plane, that's the other node. It should be 3D. You can't have a plus 2 if it's a p orbital. What's the value of the L squared operator operating on psi 3D plus 2? What would be the result? Well, L squared psi is just L squared operating on R times spherical harmonic. Since the L squared operator affects only angles, then you can, as far as it's concerned, the radial function is a constant, so you can pull it out of your operator. So that gives you L squared y. And y, spherical harmonic, is just an eigenfunction of L squared with eigenvalue of L times L plus 1 h bar squared. So, and that gives you back your y. And this is your eigenvalue. That's just going to be equal to, in this case, for a d orbital, L equals 2. So r y times 2 times 3 h bar squared. So that gives you 6 h bar squared, and ry is just psi. Okay, so we say that these atomic orbitals have a well-defined magnitude of angular momentum equal to L times L plus 1 h bar squared, square root of that. Okay, and they have a well-defined z component, and which is just going to be, in this particular case, L sub z operating on psi of 3d plus 2 will just give you mh bar times psi 3d plus 2. And your m in this case is just plus 2.